Hello everyone, I am Uttam Satpute, Professor and Electrical Engineering Department at D.Y. Patil Pratishthan's College of Engineering. This is unit video number 6 on traction moment and energy consumption of the subject electrical generation and utilization of 8th semester. In this video, we'll continue with the forces, tractive forces that are acting on the train to propel it. So in the previous video, we have seen there are the four type of forces so that I required to propellate the train. The first is the force on the wheel to rotate it for angular acceleration. Then there is a force required for linear moment, so what we can call it as for acceleration, force required for acceleration. Then we require a force for overcoming the gravitational force, and there is a force required to overcome the train resistance due to the track resistance or wind opposition, etc. Now, in the previous video, we have seen the force that is for angular acceleration of the train. Now, in this video, we should see the other three forces. So, this will call total the force, what we call it as total active effort or total tractive force required to propellate the train. So here it is, the given equation is given. You can see the total force F, it is equal to Fa plus Fg plus Fr. This is the force tractive effort required for the train moment. Now let us find out the equation for each of these forces. So the Fa force, it is given by here, the equation you can see, Fa is given by mass into acceleration. This is, we know that the force is given by mass into acceleration. Suppose if I have a train, now I'm showing it with simple block, and the weight, the mass is m, and I want to move it with an acceleration a, or here now it is alpha acceleration. Then what is the force required? So the force required, it is equal to mass into acceleration, m into. Now m, it is given as, now it should be in terms of kg, but here we are given a mass as w, it is in tons. So 1000 kg, 1000 kg, it is equal to 1 ton. So for that we are multiplying it by 1000 here, so that w, which is given in terms of tons, get converted into uh, into kg. And the unit of acceleration, it is in kilometer per hour per second. So second. Now we want this acceleration in meter per second square. We require in meter per second square, so that our F, whatever we get, it is in terms of Newton force. So to have the unit Newton, so the acceleration need to convert into meter per second. But alpha, it is given in kilometer per hour. So we have to convert it into meter per second square. So what we do, this alpha, we are multiplying it by 1000, so that it gets converted to meter, divided by 3600, that is to convert this hour to seconds. And what this second is already there, so second square it will convert. So this is what the equation we have to use. So if you use all these, so finally we get this equation, that is 277.8 w into w is the weight of the train in terms of tons, and we have to remember these units. And alpha, it is the acceleration, at what acceleration we want to move the train, and it is, the unit is kilometer per hour per second. Okay, so this is the equation we can find the force required for acceleration. But here there is one important point, that this w, what the weight actually we have taken, actually now this fa, uh, fa, it is included with this force that is acting on the wheel. So the weight actually it is a little bit increased by 8 to 15%. So to take into account the force acting on the vehicle, on the wheel, force for angular acceleration. So the weight it is increased, what we call it as effective weight. So the effective weight it is actually taken as 1.5 to 15%. So for example, 1.15% into W, that is the W is the weight of the train. So it is taken 8 to 15% more than the weight of the train. That is what we call it as effective weight, to take into account the force for angular acceleration. So this is the equation what we have to remember. And force required for acceleration, and we is the effective weight of the train, which is taken as 1.15 into W. Okay, so now let us come to the next force, that is the tractive effort for overcoming the gravity. Now here, suppose this is the train what we have, and its weight is W. The weight is W, and this is the force which is acting down because of the gravitation, W sine theta. So our force what we are giving for, we have to overcome this force, that is what we call it as Fg, which is equal to W into sine theta. Now here what's small g, W, as we know that it is in turns, so it is multiplied by 1000 so as to convert into kg. And sine theta, normally this is given by declination. It is expressed in terms of gradient. So the gradient it is written as G is equal to sine theta into 100. G it is in percentage, so it is multiplied by 100. So sine theta we can write it as G by 100. So this one and one get cancelled, so two get cancelled, so it is 10 Wg. So this is the equation here it is written, and it is multiplied. Now this weight actually it is mass into acceleration. So gravitational acceleration it is taken into account, 9.8 9 point this one 9.81. So it is multiplied by 9.81 so as to take into the gravitational acceleration. So this is the equation Fg, we have to remember it is 98.1 W into G. W is the weight of the train in turns, and G is the gradient. Okay, gradient of the slope, it is in terms of percentage. That we have to remember. Next one is the tractive force for overcoming the train resistance. This is very simple actually. Uh, we have to remember this equation. So W into R. So this is the tractive effort required to overcome the train resistance. It is W into R. W is obviously the weight of the train in turns. Okay, into R. So this R it is taken as resistance of the train in terms of turns. It is in terms of Newton per ton. It is taken as Newtons per ton. It is taken in Newtons per ton. So in numericals, usually they will give the value of R in terms of Newton per ton. So you can simply multiply by weight, then we can get the tractive effort required to overcome the train resistance. So this is the final equation for we have for the total tractive effort required to overcome the to populate the train. So we have to remember this equation: 277.8 WE alpha, plus or minus. So plus if it is up gradient, and minus if it is down gradient, 98.1 Wg plus Wr. So this equation we have to remember for calculating the total tractive effort required for the train movement. And if this tractive force, if you multiply with the distance, then we will get the energy. Then we will get the energy. We will see that how energy can be calculated from this tractive effort in the next video. Then the next point, how do you find the power? So as we know that, as I told, that how we can find the energy. How we can find the energy. So the energy it is given by work done. What we call it as energy or work done. So E is equal to F into distance. F into distance. But if you divide it by time, then we'll get a power. We know that energy by time, so it is multiplied divided by time, but distance by time, it is velocity. So F into velocity will give you the power requirement. So it is here the same, it is tractive effort, what we have find out in the previous equation, Ft into the speed. Then we can find what is the power required for driving the train. So this is how we can find the power required for driving the axle. Okay, so this much is there in this video. We'll continue in the next. Thank you very much.